How's it going, Tyler?
Hey, how's it going, Freddie? So it's all right for me. I'm a little tired. How about you?
Yeah, it's going all right. Um,
We just got the project for pre-calc recently, and we have to show our class these projects on Friday.
mhm,
It's due in 13 days, I think. So it's really crunched for time, and this is their first project, so it's going to be rough.
I see.
Yeah,
Sorry to hear.
yeah, yeah. What are you gonna do?
Well, you sprinkle points around, and that's it. That's how I make
And just
the
call it a
project.
day. Sprinkle points. Yeah. I mean, yeah. I'll probably, I'll probably do that. But yeah, it's just gonna be stressful to grade that, anyways.
Well,
Yeah,
not really. Just make sure nobody's very unhappy. If they're a little bit unhappy, nobody cares. But if they're very
right.
unhappy, then there's a problem.
That's a good point, Manzelos. Duly noted. Yeah, yeah, that's true.
I like Mancelo's take that it's just like emotional control. Like you
I mean, to be fair, all these projects are hard to grade, and
Yeah,
you don't really know. At least
yeah,
I last time I didn't really know how to have fixed. I don't know, like there was this rubric or there was some
yeah,
vague guidance, but after that, should I take off a point here or should I not?
right, right. I think the idea is just to like grade completely by the rubric, but even more this time if they include, I'm just probably gonna give them points. I'm not gonna be picky about it. Yeah.
That's why I have an in-person exam and there's nothing for me to check. I just take the test, correct or not, I put the grades and I move on.
Right. Yeah. Yeah. Yep. That sounds ideal. Yeah, that's probably what I'm gonna end up doing.
that the number theory seminar time today caught me off guard. I don't know if maybe that's been listed on the calendar, but I didn't realize it until I got the email and I was like, oh, okay, I guess I'm going to this.
Did you attend it?
Yeah, yeah.
Nice. Yeah, I saw that on the calendar for a while, but there's no way I can attend that. I teach class at that time, so I
Yeah.
just resigned. I just accepted my fate. I was gonna miss it today. Was it
I was
good?
teaching too and I was supposed to end at 11:10. But 11:05 I was out here at Zoom remotely.
Yeah, yeah. I had two classes. I have 10:20 to 11:10, and then 11:30 to 12:20. So I
Oh,
just
so it's back to back.
yeah. There's no chance of me attending that. I do have a question. So last year we did something over the summer, like read some CM stuff in modular forms. Would you guys be interested in that for this summer as well?
I will be down, and this time I will do it because last
Yeah.
time I backed out.
I remember that. Yeah. Okay. Then maybe I'll send an email about that later.
Hey, well, that sounds nice. All right, sorry I'm late. I was actually recording an asynchronous lecture for my other class, and it went a few minutes later. So too many lectures. All right. So yeah, I guess we should address global class field theory. That's what I'm doing today. I left a little bit of the rest of chapter 15 for the following lecture. Yeah. Well, you know, some things are easier when you don't prove them at all. So part of this is going to go pretty fast, I guess. So yeah, so now we're actually trying to do the class field theory formalism for a global field, right? So we're trying to show that the ideal class group is a target for global class field theory. Okay, so first few results. So this sequence here that's coming from taking Galois cohomology of the short exact sequence that defines the Adel class group. The H1 here would be H1 with coefficients in the Adel class group, which we said before was equal to 0. And so yeah, so this sequence is exact. Okay. Again, this is closely, as we're about to see, this is closely related to the sequence defining the Brauer group of a local field, global field, because this H2 really is just the direct sum of all the local Brauer groups. And so this looks very much like the Arden-Brauer-Hasse-Noether sequence, and that's what's happening. So I think this is just an immediate corollary from this, that the invariant map, again, so the invariant map is basically just defined if this is the direct sum of the local Brauer groups. Well, we have an invariant map from each of the local Brauer groups into Q mod Z, so I can take the direct sum of a bunch of maps, and that'll land in Q mod Z as well. That's the global invariant map. And so it follows that the global invariant map induces an isomorphism on H2 second Galois homology with coefficients in the Adel class group into Q mod Z. And so again, this is one global analog of the fact. So that, you know, it's kind of funny. So the Brauer group of a global field is not Q mod Z, as you can see. It's much closer to an infinite direct sum of copies of Q mod Z. But in the role of global class field theory, there's still something that is isomorphic to Q mod Z, which is playing the role of H2 of second Galois homology with coefficients in the multiplicative group. Instead of the multiplicative group in global class field theory, we use the Adel class group. Okay, and so yeah, I really think that this corollary, it probably is, comes from this theorem, and just comparing this theorem to the Albert Brauer-Hasse-Noether theorem. So it starts out the same way, and then we have this invariant map here. And so if you kind of put the second exact sequence below it and realize that it factors through correctly, it's just a tiny little diagram chase that I'm skipping to get that. Okay, so that's satisfying. So because of that, if we have a finite G Galois extension, okay, so we've been looking at this relative Galois homology in the Adel class group. In particular, we're looking for a kind of Tate-Nakayama type of setup, right? Right. So for Tate-Nakayama, we want the H1 to be trivial, and then we want there to be a class in H2 that, at least upon restriction to every cyclic subgroup or something, has order equal, restriction to every cyclic subgroup generates the second Galois homology and has order equal to the order of the group. And so that's what's happening here. So if you just analyze the inflation restriction sequence here, so right, so at this moment, we know that this invariant, we just said that this guy is isomorphic to Q mod Z via the global invariant map. So is this one isomorphic to Q mod Z via the global invariant map? And then earlier, we mentioned the way that what happens to these maps under restriction. Just like in the local case, if you restrict to a degree n extension, what happens? You know, this is the kind of functoriality of the Brauer group that we were talking about, right? So what happens? What happens on the invariance? Well, the corresponding map on endomorphism on Q mod Z is multiplication by the degree of the extension. Okay, and so therefore, just, you know, because these are isomorphisms and this is this is an exact sequence, it follows that the kernel of this map is isomorphic to the kernel of that map, which is evidently the subgroup of order L over K, so 1 over LK Z mod Z. Okay. So yeah, so H second Galois homology with coefficients in the Adel class group is a cyclic group of the right size. Okay. Right, and so in particular, the invariant, right, so this is what I just said. So the invariant map gives us that isomorphism. And so there's our fundamental class. So we have a fundamental class U of L over K inside this cyclic group. Well, we know what the group is, and we have this cyclic group has a canonical generator, namely 1 over L to the K plus Z. And so that's what the fundamental class is here. So it's the class that gets mapped under this global invariant map to our distinguished generator of our finite cyclic group. Okay, and so now the class field formalism kicks in finally with the Tate-Nakayama stuff. So if I have a finite G-Galois extension, then coupling with this fundamental class induces an isomorphism. Okay, and so so I'm coupling with the fundamental class, and this is I'm starting with H minus 2 with coefficients in G, just like I did in the local case, and that Tate H minus 2 is H sub 1. H sub 1 with coefficients in Z is the abelianization. That was from the very beginning, almost the very beginning of the course. So that's at one end. At the other end, that should be a Tate H0. And so that a Tate H0 is, as usual, the norm co-kernel. Okay. So again, this is what makes it all. This is like the single most important part, right? So the norm co-kernel is isomorphic to the abelian Galois group. Okay, and so it's more useful though to think of the map going in the other direction. So it's an isomorphism. So take its inverse isomorphism. I'll call that the reciprocity map, omega L over K. For some reason, Harari, I think at this point, I think he calls this map the norm residue symbol. Well, I don't know. I guess I see a norm, but I wouldn't. For me, a norm residue symbol is like a Hilbert symbol or something like that. So anyway, I wouldn't call this a norm residue symbol, but maybe somebody would. Anyway, so right. So this inverse map, that isomorphism. Well, we already defined a global reciprocity map on the Adel class group. And so I claim that what's happening here is that that the kernel of this map is precisely K star times we already knew that was part of the global reciprocity theorem, the K star. Let me flip back and show you that, I guess. Yep. So global reciprocity law, we didn't prove it. The global reciprocity map factors through the Adel class group. So right, and so the claim is that this inverse map is obtained by passing to the quotient from what I was previously calling the same thing. Right? And what is this map? This map is just an Adel is a direct product with some restrictions. And so this map really was just the product of all the local reciprocity maps once we map the local Galois group into the global Galois group using the isomorphism between the local Galois group and the decomposition group. Okay. And so the first part of that, again, really was Tate-Nakayama. You should look back at that amazing result of group cohomology. And then the rest of this really just the fact that it was the second thing was the first thing factored through. That follows from the definition of the local reciprocity maps. Okay. So yeah, I mean, a lot of this approach to global class field theory, by the way, is really leaning heavily on local class field theory. Of course, but just to mention, that's not the way that it happened historically. Historically, global class field theory was established first by much more, I mean, depending on your taste, but a lot of extra work was being done in order not to be able to lean on the local class field theory, but is in fact the fact that there's a lot of local global compatibilities is really an advantage of this approach to class field theory. We'll see maybe, oh no, we're not going to see it in this lecture. It's going to be in the last lecture. Okay, we'll see how local global compatibility. Well, let me just stop it. What am I going to prove? We're going to prove that the primes that split in the Hilbert class field are precisely the principal ones, right? So this main result about, not main, I mean, one of the key results about the Hilbert class field, and we will prove that, and the proof involves looking at local reciprocity. Okay, so let's see. Right, so again, we have all these compatibilities on the reciprocity map, sort of same as the ones that we were much more careful about in the local case. So we pass to the limit, and then pass to the limit over what? Yeah, so I have each of these maps, right? And so one way to, you know, I can pull this back to CK, of course, and so I get a map from CK into GAB. But I know that the kernel is the you know, is the norm, and then these are going to be compatible with passage to extensions. Okay, in the same sense, exactly the same sense that we wrote down in the local case. Okay, and so then just by passing to the inverse limit on the target side and using the fact that they're compatible on the source side, this gives us our reciprocity map. Yeah, so for some reason, Harari now renames, I mean, he took something and then he called it, you know, there was like a parenthesis, then he called it omega, and then he names this map rec, REC. And it's like, okay, too many names. Like, sure, it's the reciprocity map, but we were just calling it omega, so why don't we continue to call it omega? Okay. And so, yeah, it follows from, it does follow from the formalism that the image is dense. I mean, why is that? Because it was, by design, it was surjective onto every finite quotient. Okay? So if you just think about the way the topology of profinite groups work, if you have a map and you know that after composition with the quotient by every open subgroup, then the map is surjective, then the image is dense. That's kind of what's the point. Every non-empty open subset of a profinite group contains a coset of a open subgroup. All right, so yeah, so by construction, the map has dense image for the second time. And again, the kernel is, I mean, you can see what the kernel was. We were passing to the limit on all these finite level maps that have all the kernels, the norm. And so evidently, the kernel of the entire map is the intersection of all of these norm subgroups. Okay, so that's called the subgroup of universal norms, which is kind of reasonable because they are literally the elements that are norms from every finite abelian extension. Okay, right. And so this, again, this is all familiar. So when K was local, this was exactly what happened. And then we showed that this kernel, this subgroup of universal norms, was the trivial group, right? How did we show that? We showed that essentially by looking at this Lubin-Tate stuff and finding being able to work out exactly what this norm subgroup was for a big enough big enough class of extensions to see that basically we could get any higher unit group as a norm subgroup, and the intersection of all the higher unit groups is trivial, more or less. And so, yeah, so what happens this time? Well, this time it works out differently, and it actually works out very differently. I kind of telegraphed this a few lectures ago. I think I was afraid I wasn't even going to get this far, but I underestimated how much quickly it goes when you prove nothing. So, okay. So we're going to address that just in a second. So here, though, if I have a finite abelian extension with Galois group G, then the first Tate cohomology is it has order L over K. This was called the axiom of class field theory. It was a result. We didn't have time to prove it, but for cyclic extensions, and now we have it for all abelian extensions. Okay. Well, of course, that's a corollary. I guess I'm pausing because Well, that certainly follows from what we just said. So let me just pause to point out that that certainly follows from what we just said, because, well, this is the Tate H0, it's the norm co-kernel, and I just said it was isomorphic to the abelianization of the Galois group. So if it's already abelian, then yes, I have an isomorphism from the norm co-kernel to the group itself, and so evidently the size of the norm co-kernel is the size of the group, which is the degree of the extension. Okay, fine. All right, and so let's say that call a subgroup of CK containing, what are we calling it? A norm subgroup. Okay, so kind of same as before. So a norm subgroup are the groups that are norms from finite abelian extensions, and then it follows from the formalism that if you were to take a finite Galois extension, then the norm subgroup would be the norms from its maximal abelian subextension. It doesn't get any smaller. Okay, and so again, I'm not doing this nearly as carefully. It's clear that they're finite index. That's for the third time. That's what the index is. There it is. It's finite. One should also argue that they're open, and we're skipping that. And then this lemma is very similar to what we saw in the local case. So a subgroup containing a norm subgroup is a norm subgroup. So again, there's a Galois correspondence. If you just go among norm subgroups and the Galois groups of their extensions, then there's this nice inclusion reversing Galois correspondence that we saw in the case of local fields, right? So the lattice of subgroups containing a norm subgroup is like or anti-isomorphic, order reversing isomorphic to the lattice of abelian subextensions of the corresponding finite abelian extensions. So that's just formalism. That certainly holds here as well. And in particular, a subgroup containing a norm subgroup is a norm subgroup. The intersection of two norm subgroups is again a norm subgroup, but that's what Harari says. But okay, if we're here, I can tell you what it is. So again, this is kind of the way the Galois correspondence works, right? And so if you intersect the norm subgroups of two finite abelian extensions, L1 and L2, then that should give you the norm of the compositum finite abelian extension. All right, again, this really is kind of a Galois theoretic statement if you think about it. Okay, let's see. Right, and so I don't think this is going to come back later, but it's kind of interesting that before it followed from the formalism so far that if you take an extension that is not necessarily abelian but is Galois, that it is whatever its norms are going to be the norms from, like I said, the maximal abelian subextension. It's also true that if you take a separable extension that's not necessarily Galois, then the norms are going to be a norm subgroup, which means it's also going to be the norm from some abelian extension. Okay, it's kind of interesting, but I don't think it probably comes up for something, but not. It just doesn't come up at the level of resolution that we're working at today. All right. So yeah, now just really big things from now until the end, I think. So now I'm going to take the norm 1 or absolute value 1 Adel class group. So again, there's this different type of norm, kind of absolute value type norm that we defined before. It was literally just the product of all the local norms, which is not really an infinite product because of the restriction on the infinite product on the Adels, and the product formula precisely says that this Adelic norm map factors through to the Adel class group. Minor thing, before I was calling this CK super 1 because they're the guys with norm 1. Now following Harari, I will call it CK super 0. Why am I changing my notation? Because I'm about to use CK super 1 for something even more important. It's going to I'm about to define these kind of congruent subgroups of the Adel class group corresponding to moduli. And so one is a modulus. And so that notation is being used for something else. This is really, I still don't really like the notation because to me, if I do CK super 0, that makes it look like the identity component of this topological group. And it is somewhat related to the identity component of the topological group. And sometimes it's equal to the identity component and sometimes it isn't, as I think we talked briefly about before. So I kind of don't like the notation, but too late, I'll go with it. All right, so here it is. Here's the global existence theorem. So you take a global field. This is what you wanted to hear. The finite index subgroups of the Adel class group are precisely the norm subgroup, so finite abelian extensions. Moreover, if two finite abelian extensions have the same norm subgroup, then they were equal. Okay, so what is this saying? This one really is saying that the reciprocity map induces an isomorphism from the profinite completion of K to the abelian Galois group, if you think about it. Because what is the profinite completion of a topological group keep in mind about the topological group? It keeps in mind the finite index open subgroups, right? So that's the idea. The profinite completion map on a topological group is generally neither injective nor surjective, but it induces a bijection on the lattice of finite index open subgroups. Okay, so that's kind of what the profinite completion is doing. It's taking the same finite index open subgroups that you already have, and then defining the topology in terms of those finite index open subgroups. Okay. Okay, so yeah, so this one is really telling us the main statement of class field theory. Okay, and so the proof in Harari takes about 2 pages, so it's not nothing, but it's been mostly developed up until this point. Would certainly have wanted to give the proof if we had time. However, more surprisingly, he does not give a complete proof in the function field case. So in the function field case, he does not prove this result for finite index open subgroups whose index is divisible by P in characteristic P. Okay, so he explains how this follows from a later topological assertion about CK. I'll show you what that assertion is in a second. But he doesn't prove that topological assertion about CK. He refers you to Arden Tate. So I don't know. Actually kind of makes me feel a little bit better that we're skipping the proof, because if we've gone through all of it and then, but anyway, sure you can. I didn't realize it was so much harder to, I don't know. So this makes me, I honestly don't know. Like, is it actually that much hard? It makes me think that it's probably harder, you know, significantly harder in that case, because he does a lot of stuff in the function field case anyway, or I don't know. It'd be interesting to look at someday. Okay, so remember I was saying that CK0 kind of looks like it should be the identity component of the topological group, but that's not what it is by definition. So now I want to talk about the identity component of the group. So following Harari, I hate this notation, but oh well. So DK is going to be the connected component of 1. So for any topological group, you know, you have a, you just take the connected component of the identity element. This is always a, well, this is a commutative topological group, so it's certainly normal. In general, it would be a closed normal subgroup. Okay. Since the abelian Galois group of K is, well, it's a Galois group, so it's a profinite group, so it's totally disconnected. The image of any, and the reciprocity map was designed to be continuous. Well, the image of any connected thing is connected, and if you're connected inside a totally disconnected space, you better reduce down to a single point. So it was clear from any, you know, before we did any work whatsoever, the identity in any target group for class field theory, the identity has to lie in the kernel of the reciprocity map. Okay. And so I did tell you a few lectures ago quickly what the kernel was, what the identity component was. In the number field case, it's kind of weird. There was some like there was some weird solenoid that came in, right? So there was an inverse limit of S1 under the multiplication by n maps, which was the Pontryagin dual to the additive group of the rational numbers as a discrete group. Anyway, so it depended a little bit on number of real places, number of complex places, which is very reasonable because those real and complex places are appearing as factors of the Adel group. However, just because of this norm map, the norm, this thing has a homomorphic, the Adel class group has a connected topological group as its continuous image. So it should not be totally disconnected. In fact, I'll show you a result later that explains it, that nails that down logically. And so in the number field case, there is, the connected component of the identity is a finite product of different groups. Possibly there's this weird solenoid thing, but always R is a direct summand. Okay, so what am I saying? I'm saying for sure in a number field case, the identity component of the Adel class group is not trivial. It's R cross something. Okay, and so what am I saying? Therefore, and I think I said this before, therefore the reciprocity map in the number field case is most certainly not injective. Okay. Another way of saying that is that the subgroup of universal norms is not trivial. Okay. All right, and so here's the theorem. Here's the theorem in the number field case. So in the number field case, the connected component of the identity, I just told you that it lay in the kernel of the reciprocity map. That was completely obvious just by looking at topological groups. In fact, it is the kernel of the reciprocity map. Okay. And therefore, the identity, because the kernel just formally is the subgroup of universal norms, it didn't really tell us what it was as a subgroup of, I mean, saying it's the group of universal norms is much closer to being a description on the Galois side, I think. But what is it as a subgroup of the Adel class group? It is the connected component of the identity. Okay, so therefore, in the number field case, the reciprocity map fails to be injective, but it fails to be injective kind of in the most obvious way. Its kernel is the connected component of the identity, so couldn't have been any better than that. However, it is surjective. Okay, so that's part of the theorem. Remember, okay, so here's a test. So in the number field case, I'm telling you the reciprocity map is surjective but not injective. What was it in the local case? Someone should tell me whether the reciprocity map was injective or not, and tell me whether the reciprocity map was surjective or not.
Is it injective but not surjective?
Yeah, that's right. So it's injective because the universal norms are reduced to 0. I mentioned that before, actually. And the reason that it's not surjective, well, is because the target group was K star, which is unit group cross Z. And so, well, that group is not profinite because it's got the Z factor. And so the map to its profinite completion is basically profinitely completing the Z to Z hat. Okay. On the Galois side, what does that mean? The Z hat is definitely a quotient of the abelian Galois group of a local field. That's the Galois group with a maximal unramified extension. Whereas the reciprocity map, when you take the reciprocity map and you restrict it to the unramified extension, you get things which are in the cyclic subgroup generated by the Frobenius map. So which sounds fine, but from profinite Galois theory, again, the automorphism group of the maximal unramified extension of a local field over that local field, the Galois group is Z hat. So there are automorphisms that are not literally just a power of the Frobenius, they're a limit of that in some sense. Okay, so that's the point. The point is that the map is not surjective because the reciprocity map is only giving you actual integral powers of Frobenius, not like profinite, not profinite limits of powers of Frobenius. Okay, remember that, because this is what the end. So in the number field case, Zoop, exactly the opposite. In the number field case, the reciprocity map is injective, is not injective, but it is surjective. Okay. Right, okay. What about the function field case? Oh, what terrible tragedy happened there. It's kind of funny. There was like a stain on my couch last night that I removed. I wonder if this has something to do with that. Anyway, okay. In the function field case, it turns out that the Adel class group is totally disconnected. Again, so here's the result that I was saying before, that, you know, once you enunciate it, it makes things. So in general, of course, like the image of a connected thing is connected. That's like the first thing one of the first things you prove in topology. The image of a totally disconnected thing most certainly does not have to be totally disconnected if you're just working with topological spaces, like I don't know, the unit interval is a continuous image of the Cantor set or something. Not or something, that's literally true. But if you take quotients by topological groups, things get better. So this is a result. Harari mentions it, I'm sure. I think it's like probably in Bourbaki general topology. So if you take a locally compact, totally disconnected group and you mod out by a closed subgroup, then you retain your local compactness and your total disconnectedness. Okay. So that's therefore the Adel class group is totally disconnected. You look back at the definition of the Adel class group, it's a restricted direct product of totally disconnected groups. So how in the world can it be anything other than totally disconnected? You can easily prove that it is. And so, yeah, and so therefore I'm taking a totally disconnected group and I'm modding out by K star, which is discrete enclosed in the Adel group. And so therefore the Adel class group definitely is totally disconnected. What is the image of the norm map that, I should say the absolute value map better. In the number field case, the image of the absolute value map was all positive real numbers because we had these Archimedean places. If you just take Adels, which are trivial at every place, and then whatever you want at one either real or complex place, well, then you're just restricting to the norm map on that one completion. And of course, the norm map on R is surjective onto the positive real numbers. And of course, the norm map on C, absolute values, I should be saying, is surjective onto the positive real numbers. In the function field case, everything is a power of Q. And so the norm map is going to land in subgroup of Q to the Z. In fact, I mentioned this because it comes up in what we did last year. So if you had a degree 1 place, equivalently, if your curve had an FQ rational point, then you could use that one FQ rational point, again, to see that the image of your norm map has to be Q to the Z. Even if you don't, though, by this theorem of Schmidt, the index is 1. What is a better way of saying that? The norm map in the function field case is in fact, excuse me, the norm map in the function field case is kind of is factoring through the divisor map. So factoring through the map. So if you take an Adel, to an Adel, you can associate a divisor. We're about to do that in the number field case later in this lecture or early in the next lecture. But kind of in the obvious way, you just you just by looking at the valuation of the local component, that gives you your divisor. And then the norm map here is literally just Q to the degree of the associated divisor. And so what am I saying? I'm saying in the case of a finite field, do I have a divisor of degree 1? Yes, that's Schmidt's theorem. Okay, so anyway, so the image really is Q to the Z, which is isomorphic to Z. Okay, so what? So what? So here's the answer. This is the theorem. that Harari doesn't prove, he refers you to Artin and Tate, and he uses this to prove the global existence theorem in the function field case. So in the function field case, the reciprocity map is injective, okay? So this is just like the local case. That is, the subgroup of universal norms is trivial. And it's kind of, I mean, one way to say it's really the difference between the connected components. So in the number field case, we just said that the subgroup of universal norms was the identity component. It just happened that the identity component contained a factor of R, so was not trivial. Well, in this case, if the subgroup of norms is universal norms is trivial, well, I just said the identity component was trivial. So sure, the subgroup of universal norms is still the identity component. It just happens to be trivial. On the other hand, as far as the image is concerned, this works out exactly the same as what I was just revealing in the local case. So here we have a yeah, it's very similar. So here the cyclotomic extension of the function field is obtained by adjoining all roots of unity in the ground field. That is an everywhere and ramified extension. It's not necessarily the maximal everywhere and ramified extension. Depends on what the function field is. But again, k-sic over k has Galois group z hat for the exact same reasons. And so if you have an automorphism of k-ab over k, you can restrict it to fq bar, right? And therefore that automorphism will lie in the z hat automorphism group of fq bar over fq. And so exactly the same thing happens. The things that are in the image of the reciprocity map, when you restrict to the maximal cyclotomic extension, well, that's, then you're getting the full automorphism group of k-sic over k is z bar, and the image of the reciprocity map is only giving you z. Okay, so it's the same thing basically. All right, and so that shows you that in some sense it's funny that in the function field case, the behavior of the reciprocity map is much more closely analogous to the local case, irrespective of the characteristic, than it is to the characteristic 0 global case. Okay, anyway, so this is the unproved fact. And then he says it this way. I mean, I'll write it. I don't know. I mean, is this a nicer way to say it? I don't know. So you have a short exact sequence from the reciprocity map into the maximal abelian extension into z hat modulo z. Like, yeah, I mean, again, that follows pretty closely from what I was just saying, right? Yeah. Okay. This doesn't seem that helpful because this is a terrible group. I mean, z hat is dense. Z is dense in z hat. So like, what the hell is this quotient? All right, but just to be, so as in the local case, the Adel class group, the target group injects into its profinite completion, and what do you need to do? Injects but is not equal to. And what do you have to do to get from the group to its profinite completion in a slightly more complicated way, but still essentially, this group has an obvious quotient, has z as a quotient. Oh, that's where this was coming from. Ah, now I see why I said this before. Yeah, so this group has z as a quotient. Ah, I see. Yeah. So this, which should not, even topologically, I guess is the point. So this thing here, if we mod out by a closed subgroup, we get z, and that actually shows that it's not compact. Because if it were compact, then any continuous image would also be compact. But this is z in the discrete topology. Okay, so that's the point. The point is, just like in the local case, I took my topological group, and as a topological group, it had a z quotient. That's no good, right? Every quotient of a profinite group should be compact, and that's the only problem. If you take your z quotient and complete it to a z hat, then that gives you the profinite completion of the whole group. Okay, so now, yeah, I better just keep going. I have a lot to talk about. I think they'll probably go until at least until 3. So strap in or watch it on later on video. So now I want to talk about moduli and array class fields. Harari only does this discussion in the number field case. Again, boo, but also, I mean, you can do it in the function field case. There are some minor differences. On the other hand, we have no time, so I guess I would probably only do it in the number field case anyway. I do this in my number theory too, but it's super important, and now we sort of understand it better, I think, or have a chance to understand it better. So let's talk about it. So what's a modulus for a number field? It's a strange looking object at first. It's kind of a formal product of a finite part and an infinite part. So M0, M infinity. In other words, you just have to give me both. So M0 is a non-zero integral ideal, so non-zero ideal of zk. So therefore, you tell me what bunch of prime powers, right? And then M infinity is a subset of the real places. Okay, so that's fine, I guess, but that sounds kind of weird. So by the end of this page, maybe you'll understand why we're making this definition. So a slightly better formalism for moduli maybe is that a moduli is a certain type of function from the places to the non-negative integers, okay? So what are the properties that we want? Well, we want it to be a 0 at almost every place, okay? And so at the real places, it can only take the values 0 and 1, and at the complex places, it can only take the value 0. So maybe I'll pause for like 20 seconds, and so you can realize that this definition of the modulus is equivalent to the definition of the modulus that I gave you before. Right, so if I give you this function, you can give me a set of real places, namely the set of real places for which MV is equal to 1 and not 0. And you can give me a non-zero integral ideal. The integral ideal is going to be the product over all V of PV to the MV. Okay. One slight advantage of saying it this way is that it shows that there's a natural partial ordering on the moduli. So these are just two functions into an ordered set. So I could say that one is less than or equal to the other if one of them is less than or equal to the other at all points. Okay. And then for whatever it's worth, this is a lattice. If I wanted to take the maximum of two moduli, I just take the maximum place by place. If I wanted to take the minimum of the two moduli, I could take the minimum place by place. Okay. So it's not totally ordered, but I can take the min and I can take the max of finitely many elements. Obviously can't take the maximum of all collections of elements. Okay. And so again, just to fix ideas, if k is equal to q, then a modulus is either determined by a positive integer n, because that's what non-zero integral ideals in Z look like, or it's determined by a positive integer n and I just tack on infinity, the real place. Or if I had a real quadratic field, I don't know why, is this helpful? We'll see. So it could just be a product of prime powers, primes in the ring of integers, or it could be the first real place times the product of prime powers, or it could be the second real place times the product of prime powers, or it could be both real places times the product of prime powers. Okay, fine. So what's happening here? The moduli are really parameterizing open subgroups of the completion, sufficiently small open subgroups of the completion. So now if I have any non-Archimedean place, as I've done many times before, U super 0 will just be the full unit group. So unit group of the evaluation ring. It's a compact group. And then for all n greater than 1, UN will be the higher unit group, our good friend in this course. And so, I mean, that's what it is. Things that are congruent to 1 modulo pi to the n. Okay. Otherwise, it's a certain ball around 1, also a subgroup. Okay. And then what's the point? The point is that the UNs are co-final among open subgroups of KV star. What do I mean? I mean, if you give me any open subgroup of KV star, then it contains UN for all sufficiently large n. That's what I mean. Okay. As I think we've used before. And then in the Archimedean places, we can do similar things, but it's not as interesting. So for a real place, I'll take U0 to just be the entire KV star. And then U1, I'll take the positive real numbers. These are both open subgroups. But the point is that the real numbers the non-zero real numbers doesn't have that many open subgroups. In fact, it has exactly 2 open subgroups, and these are the open subgroups. Right, our positive real numbers are isomorphic to the real numbers. The real numbers have no proper open subgroups. Okay. And then in the complex numbers, that's even worse. If you think about it, there are no proper open subgroups of the complex numbers under multiplication. There's some interesting closed subgroups, but not open ones. Right. Okay, so that's what so that's where the moduli are coming from. They're helping us to write down sufficiently small open subgroups in all the completions. Right. So that's what I just said. For each place, we've given a cofinal system of open subgroups of the multiplicative group of the completion. Here comes the maneuver. So for a modulus, I am now going to define an open subgroup of the Adel group. In a very obvious way, the V component is going to land in the corresponding unit group. Okay, so you see the MV is some natural number, and so at all but finitely many places, I'm getting, yeah, so what is this? At the complex places, there's no restriction. At the real places, there's only, it's restricted to be positive if that real place is included in the modulus, if not, not. At the non-Archimedean places, it is a restriction. It's always restricting it to lie in the unit group of the ring rather than just the multiplicative group of the field. So it's lying inside a compact subgroup of a non-compact topological group. It might be further restricted to lie in a larger unit group, but for all but finitely many places V, the only restriction is that it lies in the unit group. Okay. So IK of M is definitely an open subgroup of IK. It is definitely not of finite index because these UVs are even U0 is a compact subgroup sitting inside a non-compact. Okay. All right. And so since quotient maps, again, in topological groupland, things are a lot better than for arbitrary topological spaces. When you mod up any subgroup, that gives you an open quotient map. Not all quotient maps are open, but these are. And so therefore, the image of this open subgroup in the Adel class group is an open subgroup of the Adel class group. Okay, so CKM, I take my pretty transparent open subgroup and I just shove it into the quotient in the normal manner. So I take the subgroup generated by K star and I mod out by K star. Okay. So these are great. Harari calls these congruence subgroups. All right. Well, let's start with the smallest modulus is m equals 1. So MV is equal to 0. For all V, what do we get here? Well, the I super 1, again, it's no restriction at all in the Archimedean places, and at the non-Archimedean places, we're just restricting to land inside the unit group. Okay, so this is one of the basic opens that we use to define the Adel class group. Okay, I guess it's the smallest of the basic opens that we use to define the Adel class group. Okay. Yeah, it's the biggest that the I of M is going to be, and it's this, anyway, whatever. Okay. So there exists a natural surjective group homomorphism. This is actually, this is pretty much what I was just describing in the function field case. To an Adel, you can attach a divisor. Here to an Adel, I'm attaching a fractional ideal in the exact same manner. Okay. This comes up, something like this came up when we were doing Bay differentials and whatnot last semester. Anyway, so it's pretty clear. You just take your Adel, and then at each non-Archimedean place, you just use the valuation of the corresponding place to give you the exponent of your prime ideal. Okay. Notice that, I mean, this is a perfectly nice map, but it is not taking the Archimedean places into account at all. Okay. All right. What's the kernel of this map? Well, evidently I need to have zeros all over here. So evidently I need my adels to have valuation 0 at all finite places. Aha, the kernel is precisely this group here. Okay, and it's obviously surjective. You know, every fractional ideal is a power like this, and so with finitely many non-zero exponents, and so sure, what if you give me a bunch of integers, all but finitely many of which are 0, of course I can give you an adel whose valuations are those integers. No problem. Okay, so the map is plainly surjective, and it's plain that the kernel is this I super 1, and so therefore we pass to the quotient, we get an isomorphism. This is open even, as I said, so this realizes frac zk as it's a discrete. Naturally, it's topologized as a discrete group. Okay. Well, so it's about to get better though, because I have a notion of principal things on both sides. So here I have principal adels, which are coming from K, right? So I could still mod out by K over here, and that would give me C1 of K, right? But then I have an isomorphism, so I just have to figure out where do the principal adels go under this isomorphism? Someone tell me.
I mean, you do have it written there, so it feels a little
Oh,
cheap,
okay.
but
Damn.
yeah.
Damn. Someone tell me now. All right. It's been a long whatever. All right. So under this isomorphism, the principal adels map to principal ideals. Okay, so we just right. But that's amazing, because therefore this isomorphism induces an isomorphism from this, which is I think maybe I said that wrong. So this quotient is right. So if you think about it, this quotient can be viewed as the quotient of the adel class group modulo this modulus 1 adel class group. Let me just think about that for a second. That's true, right? Sure. Okay, and so that becomes isomorphic to the fractional ideals modulo principal ideals. Okay. Let me just think for a second. What's bothering me? Yeah, so I should put something. Yeah, so I should put a case star there. Okay. Yeah. Okay, now I feel better. All right, so that was what was bothering me. And anyway, but this is great. So what does this mean? This means that, first of all, this means that the CK1 is finite index in CK, even though, as I said, IK1 does not have finite index in AK, but that's fine because I passed to the quotient by this other group, so that could certainly make the index much smaller. But moreover, the quotient is isomorphic canonically isomorphic to the class group of the number field. Okay, in particular, that means that the index of CK1 and CK is the class number. Okay. And now we can bootstrap from this to other moduli. So it really is easy to see that ik of m has even before I pass to adult classes, ik of m is coming from I of k, maybe just by a couple sign conditions. That's only going to cut down the index by factors of 2, together with yeah. So this index is finite just because all these higher unit groups have finite index in the U0. Okay. So that index is finite, and so again, it definitely works that way. If you have a finite index subgroup and then you pass to the quotient by some other group in the correct manner, which I guess I forgot to do for a second there, then inside the quotient, the index could be smaller, but it'll still be finite. And so from that and what we just saw, we deduced that CKM is a finite index open sub. These congruent subgroups are finite index open subgroups of CK. And we will call the quotient here the M ray class group. Okay. Usually you would say M ray class group of K. For me, looking forward to what I want to talk about in the very last lecture with non-maximal orders, I'm going to be more careful and say that it's the M ray class group of CK. All right. Since these congruent subgroups are cofinal in the open subgroups of the adult class group, okay, that follows pretty easily from what we said, we get this result that Harari records. So it shows you why we're doing this. So the norm subgroups of the adult class group are precisely the ones that contain some congruence group. So again, the congruent subgroups are precisely a cofinal system of norm subgroups. Okay, in other words, they're cofinal in the sense of being sufficiently small, which when you go to the Galois side will mean that they're sufficiently large. Okay, so every norm subgroup, a subgroup is a norm subgroup if and only if it contains one of these congruent subgroups. But these congruent subgroups are very, they're not defined by norms from some idyllic thing. They're defined in some much more visible way, right? They're defined in a way which is more, this is kind of where the classical theory kicks in, right? These are defined in a manner that is intrinsic to K, whereas the definition of the norm subgroup is not intrinsic to K, it's with respect to some abelian extension. So that's kind of the magic, right? So now I found, just as in the local case, I found my explicit cofinal system using like higher unit groups and using Lubin-Tate stuff. This is kind of the global analog of this explicit cofinal system that I wrote down before using, there was like 2 parameters. It was like a case of MN or something, right? So yeah, so this is the cofinal system, and now everything works out great. Right, and so therefore for a modulus, there's a unique corresponding finite abelian extension, K super M. Well, what is it? Just, okay, the notation is a little subtle here. So the norms from this corresponding finite abelian extension are equal to this particular congruence subgroup, right? Every norm subgroup, that's what to say that a congruent subgroup is a norm subgroup, that's exactly what it means. It also means this, it means that the automorphism of this group is equal to the norm cokernel, well, but the image of the norms was equal to CK of M, and therefore the norm cokernel is CK modulus CK of M, which by definition is this M ray class group. Okay. So this is, finally we got somewhere. This K super M is what's called the M ray class field of K. Okay, so it's not explicit. It's explicitly defined in some sense, right? It could be why is it not explicit? Because I'm not telling you what you have to adjoin to K in order to get it. Right. All right, and so again, since the congruent subgroups are cofinal in the open subgroups of CK, what does that mean on the Galois side? It means precisely that the maximal abelian extension of K is, again, these form a directed system because the moduli are partially ordered under inclusion, okay? And so the maximal abelian extension of K is the direct limit of the ray class groups. Okay, so again, does this mean that every finite abelian extension of K is a Ray class group? No, in fact, in the next lecture, I'm going to give you a more general collection of finite abelian extensions that includes these as a special case, but every finite abelian extension is contained in a Ray class group, and so that's obviously helpful. Okay. In particular, the smallest Ray class group is when we take the modulus equal to 1. That's the Hilbert, by definition, that's the Hilbert class field. And it follows from what we just saw that the automorphism group of the Hilbert class field is equal to CL1 of ZK, which we just saw was the ideal class group of ZK. So evidently, we have a finite abelian extension of every number field whose Galois group is canonically isomorphic to the ideal class group of the number field. So that's pretty exciting. Oh, I was supposed to, okay, I guess it's been a long whatever, even still. So somewhere in my number theory 2 notes, I do talk about, I talk about Ray class fields and Ray class groups in my number theory notes. There's also a non-adelic definition of Ray class groups, which is in fact just a mild generalization of the ideal class group. You take ideals that are coprime to the modulus, fractional ideals that are coprime to the modulus, and you mod out by principal fractional ideals that are congruent to 1 modulo the modulus. And it would take me another 5 minutes to explain what that means if you haven't seen it before, but it's in the notes. Okay. So these groups, but that's kind of important. So it sounds nice. Working with the Adels is nice when it's nice, and then sometimes it sort of looks I don't know. Sometimes it's like they're nice to work with, but sometimes they're a bit mysterious. So I guess what I'm trying to say is that there's an alternate description of the group, okay, which is much more elementary. And therefore, in fact, it is true that the class groups are much easier to understand than the class fields themselves. Okay? So again, there's a very elementary description of the class group. The ideal class group is not the easiest thing to understand, right? It's easy to define, but its behavior is complicated. But that kind of gives you the wrong idea. Actually, it's much easier to compute a formula for the degree, at least, of Km over K1. I can have it either way. Maybe I'll do it like that. So there we go. So the degree of the M Ray class group over the Hilbert class, the M Ray class field over the Hilbert class field, and again, this really is proven in the notes. What is this? This M0 is just the finite part of the modulus. So this is like an Euler phi function of, if you like, of an ideal in a number field. And then there's a correction term here coming from global units. So this is the global units. And again, you don't have to say this adelically. I said it adelically because I defined it, but this is the units that are congruent to 1 modulo the modulus, if you wanted to say that in more classical language. So what does that mean? It means at real places dividing the modulus, the units have to be, we may require the units to be positive at certain real places. And yeah, we literally may require the unit to be congruent to the unit minus 1 should be divisible by the finite part of the modulus. Okay, so that's a very elementary condition. And I worked this out. So this is best. It's awesome if this unit group is finite, because then this thing is very small and is for sufficiently large M, this thing will just go away entirely. And so in my number theory notes, I work out what happens for Q, which is very easy, and I work out what happens for imaginary quadratic fields, which is also pretty easy. And then the formulas for these things for imaginary quadratic fields got used all over the place in my work with Avi Bourdan and Paul Pollack and Jim Stankiewicz on complex multiplication. Okay. So I think I timed it right. So this is a good place to stop. And so next time I have a few more things to say. I'll define the conductor of a finite abelian extension, both locally and globally, and explain the compatibility between local and global conductors. I will state 2 more properties of the Hilbert class field and prove one of them, the one I mentioned before, that prime ideals are principal if and only if they split completely in the Hilbert class field. And then in the remaining time, I want to describe a generalization of these Ray class fields where you might not have seen it, but somehow I claim that somehow all of these class fields were relative to the full ring of integers zk, or relative to the completions of the full ring of integers, which are rv. So if instead of zk you take an arbitrary z order in a number field, to remind you what that is if you haven't seen it before or forgot, you can define Ray class fields of a non-maximal order, and that gives you a simultaneous generalization of both Ray class fields and ring class fields, which are important in complex multiplication. And this is due to Campagna and Pengo in a recent paper. Okay, and that'll be it. All right, any further questions for today? All right, well, we're almost done. See you on Friday.